Good afternoon. Good afternoon. Right. So today I start by looking at an example from your textbook. Okay, I will discuss in more detail. So this is the example 7.2.1, and if you refer to the page 281. So it asks about the angular momentum of a rod as a function of its instantaneous angular velocity. Angular momentum of a rod as a function of instantaneous angular velocity, which is omega. Okay, so we have got a long thin rod of the length L. So here I can say this is my vertical line, and this is a pivot here with which the rod is hanging. Okay, so you can say, so this is a thin rod, and suppose it is, while it is oscillating, it makes an angle with the vertical line. So this is the vertical line, I can say, and then it makes an angle of theta here. Right, so consider this, if it's a uniform thin rod, and suppose this is the point which is the center of mass, in the center of that, okay, center of the rod. So here, this is VCM, the velocity of the center of the mass. CM is center of the mass, okay. So this is a velocity vector. And now, the position of the center of the mass relative to this pivot here can be written. So I would say this vector, okay, is a R vector. Okay, so this is R vector. So this is the situation which is discussed in your book. So it is a long, thin rod, length L. So I represent that this is the length L of the rod. Okay, mass of the rod is M, and the other information, it hangs from a pivot point which is the point here, you can see, okay, which I am circulating, okay, and about which it is free to swing in a vertical plane. Pivot point, and about which it is free to swing in a vertical plane. So it can swing back and forth like a simple pendulum. Right, so this is the situation which we are considering. Now, what is the angular momentum of the rod as a function of its instantaneous angular velocity? So this is the question we need to address. What is the angular momentum of the rod as a function of its instantaneous angular velocity, which the standard notation for the instantaneous angular velocity is omega. It is the rate of change of the angle theta, of course. Right. And also note that the pivot point is a fixed point. Now the angular momentum, we notice that the angular momentum notation for is L, okay, and a vector about the center of the mass. Angular momentum of the center of the LCM is the of the center of the mass, which is located here, which I've seen here at the center, okay. And now the angular momentum of the center of the mass about the pivot point, okay. Okay, now if this is the angular momentum of the center of the mass, okay, about this point here, pivot point, okay, what it is what, how can I evaluate it? This is the LCM is that quantity. We note that VCM, which I have denoted by the arrow here in this figure. Okay, let me. Okay, now VCM is the velocity of the center of the mass. Velocity of the center of the mass, which is perpendicular to the radius vector r, which you can see also from here, that this velocity vector is perpendicular to the radius vector. Okay, so radius vector is at, this is the radius vector joining the pivot point with the center of the mass. Okay, I just quickly write down, this is the center of the mass. Okay, so this radius vector is joining the pivot point with the center of the mass, and this radius vector is of course perpendicular to the velocity vector, which is velocity of the center of the mass, going perpendicular to that. Okay, now velocity of the center of the mass is perpendicular to the radius vector r. The radius vector r relative to the pivot point. Okay, radius vector r. So the velocity of the center of mass is the radius vector r relative to the pivot point, because you radius vector, the starting point or the is the pivot point. So this radius vector is the describes the, it is a position vector of the center of the mass relative to the pivot point here. Okay, so I can write down this as the relative to the pivot point. Right, now the angular momentum magnitude, which is LCM, which can be written as the magnitude of this vector, and which can be written as the r vector cross the momentum p vector of the center of the mass. Okay, so momentum of the center of the mass, okay, and this is the center of the mass. Okay, and this is the p vector of the center of the mass. R is the position vector of the center of the mass relative to the pivot. So I just write down, this is pivot here, Now this is given by RPCM, which is the magnitude of the momentum, and sine of the angle of pi by 2, which can be written as, so it is R. Okay, R is given by L over 2, because L is the length of the rod here. Okay, R is the length of this vector, which is half, because this rod is uniform and has the same thickness, same density. Okay, so the radius vector of the describing the position of the center of the mass is half the, this length is half the length L. So that's why I can write down R to be L by 2, and then sine of pi by 2 is 1. So this is 1, and this quantity is PCM. Okay, it is, we don't need to put a bracket underneath, so just put, so this is L by 2 PCM, which is the momentum of the center of the mass, where PCM is the momentum of the center of the mass. Okay, I'm just going to, so I can write down the where PCM is the momentum of the center of the mass. Okay, so it means that the LCM can be written as L over 2 PCM. PCM is equal to mass, okay, and VCM, mass time the velocity, because the center of the mass, okay, is the PCM is the momentum of the center of the mass. So the mass of the rod is m, and then velocity of the center of the mass, which is VCM. Okay, in fact we are taking the magnitude of the velocity. Okay, so it becomes uh, so this quantity is PCM. Okay, and it becomes ml over 2, okay, ml over 2 VCM. Okay, now the question is, what is VCM? Ml over 2 VCM is given by velocity of the center of the mass, because center of mass is located in the middle of the rod, so it means that it can be written as L over 2 into omega. And this expression is using VCM is given by uh, R omega, okay, R omega, just clarify, and this is equal to L by 2 into omega. So this is what I have written here, and this then becomes LCM, the magnitude of the angular momentum of the center of the mass. So it becomes 1 over 4 m L square omega. Right, so this is the angular momentum of the center of the mass about the pivot point. Okay, now if you see the motion of the rod, as seen from the perspective of its center of the mass, as seen from so it is, okay, now you consider that. So in fact, to consider that, what you need to do, you assume you are sitting here in the center of the mass. If you are sitting here, then how you see the motion of the rod while sitting at the center of the mass. In fact, if you think the center of mass, because you are located here, the rod will oscillate in one or the other direction relative to you. Okay, so it will look like this relative to the center of the mass. Okay, so I am just going to draw this as, so here we have got the vertical, and for instance rod is, so this is the center of the mass. So if the rod is, so this is your rod, okay, and this is the center of the mass, you are located here. Now if you consider, so it will say this is the center of the mass. So this is the motion of the rod as seen from the perspective of the center of the mass. Okay. Uh, Now we consider a part of the rod with the mass dm located at some location which is r. So this distance is r, and likewise on the opposite sides there is a dm, differential mass you can say. Okay, so this is r as well. So okay, if you do that, then the angular momentum dl relative, so it's denoted by dl rel of two small mass elements which I have denoted by dm on here. So this mass element here and this mass element. Okay. Two mass, each of the size of size dm, and symmetrically disposed about the center of the mass of the rod. Okay, so this is the angular momentum of these two small mass elements. So I call that dl relative is given by 2r dp, where dp is the differential momentum of one of these mass element, and the factor of 2 which you can see here, because you are adding the two contributions, one coming from r dp, okay, and the other one r dp again. And remember that if you consider the vectors r and p vectors, they are perpendicular to each other, so that's why you consider the angle to be pi by 2, and sine of pi by 2 is equal to 1. So that's why you just consider this 2r dp, so it becomes 2r, and dp is what is the differential momentum. Okay, so it becomes v velocity times dm. So this is your dp, and this can be written as 2r. Now v is velocity. Okay, so velocity of this dm here in any direction. Okay, so you can see the velocity here. So velocity is, if is given, it is given by r times omega, if you know that. So v is equal to r omega, and dm can be written as the lambda dr. So this is dm and this is v, and if you make a product of these quantities, you get 2 lambda omega r square dr. Right. Here, what is lambda? Which you can easily recognize. Lambda is the mass per unit length of the rod. So where lambda is mass per unit length. Oh, sorry for that. So just write it a bit down. So where lambda is the mass per unit length of the rod. Now, after considering this, now we consider what is the total relative angular momentum. And it is written by L subscript REL. And if you see here, okay, you are integrating this now, this expression. So it becomes 2 lambda omega angular velocity, and then now you integrate from 0 to L by 2, and with the quantity you integrate is r square with respect to r. And the reason for, because when you integrate, your reference point is the center of the mass, okay, and you are taking these differential masses along the direction of the rod, and this location of the differential mass can increase from 0 to r only, okay, because you are considering pairs of those in opposite direction. So the integration limit should be from 0 to L by 2, because the total length of the rod is L. Okay, so we can rewrite this as the endpoints of the rod are, so I can say the endpoints of the rod are at the distance of L by 2 from the CM, center of the mass. And now, because two elements are counted, two elements, which element? dm, are counted, so that's why the integration is from 0 to L by 2. So the reason for this, putting this, so it becomes L relative becomes 2 lambda omega, and when you integrate r square with respect to r and in the limit, so you get L over 2 raised to power 3, and which can be written as 2 over L power 3, and then when you integrate, sorry, there is a factor of 3 then as well when you integrate, okay, because it becomes r raised to power 3 divided by 3, okay, when you put the limit, then it becomes L over 2 raised to power 3, and this is a factor of 3 which appears in the denominator. So it is 2 by 3, right, and lambda omega, and 2 by 3 lambda omega, and this becomes L raised to power 3 divided by 8. So it becomes 1 over 12 lambda omega L raised to power 3. And here we also notice that lambda is what it is, the mass density per unit length, mass per unit length of the rod. So if the mass of the rod is m, so if you divide m by L, it becomes the lambda. So it means that L relative, okay, so becomes 1 over 12 lambda lambda I can substitute m over L, okay, so it becomes m over L, and then we have got omega L raised to power 3, and if I simplify this, it becomes 1 over 12 and m L square omega, because 1 L cancels with L raised to power 3. So right, so this is the expression. The angular momentum of the rod about its center of the mass so the angular momentum of the rod about its center of the mass is directly proportional to, sorry, so it's directly proportional to the angular velocity of the rod, as you can see, okay, and report to the angular so here it is means R rel is directly proportional to omega, okay, so this is the notation for direct proportionality. The constant of proportionality you can easily see in this expression is given by 1 over 12 ml square. The constant of proportionality ml square divided by 12 is called the moment of inertia. Okay, I write it in capital, moment of inertia. And the notation for ICM, because it's moment of inertia uh, of the center of the moment of inertia of the rod about its center of mass, ICM. So ICM of the rod about its center of the mass. Right, so it means that the equation becomes, so what is the moment of inertia? It is the moment of inertia is it plays the role of it plays a role in rotational motion, which is similar to that of the inertial mass in the translational motion. Okay, so and there is a direct connection, so I will show it to you. So the plays a role, moment of inertia, it plays a role in rotational motion similar to that of the inertial mass in the translational motion, to that of the inertial mass in translational motion. So if you see that connection, what it's saying is that the RL is given by ICM, moment of inertia of the rod about the center of the mass times omega. And if you compare this to that, this is the angular momentum, okay? And if you consider the linear momentum, it is the mass times velocity, okay? Now you can see the comparison. This ICM, which is the moment of inertia, it is playing the role of the inertial mass here, m, and the angular velocity is being compared to the linear velocity. You see, and the angular momentum is being compared to the linear momentum. So you see the relation has got similar structure as it is the case for the momentum expression here, which is connected to the velocity and the inertial mass. And now the similar expression appears here for the angular momentum, but the connection is now involved the moment of inertia times the angular velocity. Okay. So the total angular momentum of the rod is L total, is given by the angular momentum about of the rod, uh, angular momentum of the center of the mass relative to the pivot, so LCM plus L rel. Okay, so just a quick reference to so here you can see that the LCM is the angular momentum of the center of the mass about the pivot point. Okay, so here the total momentum, total angular momentum can then be written as uh, there are two parts to it. So one part is the angular momentum of the center of the mass relative to the pivot. So this is the angular momentum of uh, the center of the mass relative to the pivot. Okay, and this one is the angular momentum relative to the center of the mass. So L total can then be written as if you see there are two expressions, so LCM, which we evaluated above, which we remember that there is LCM, which was 1 over 4 ml square omega. Okay, now if you consider that, and then L relative was ICM omega, which was coming out to be 1 over 12 ml square omega. Okay, so I add them together, so to get the total, so it will becomes 1 over 4 ml square omega plus 1 over 12 ml square omega. So it becomes 1 over 4 plus 1 over 12 and ml square omega. So it is then, if you add up these fraction, it becomes 1 over 3 ml square omega. So it says that the total angular momentum total angular momentum is directly proportional to the angular velocity of the rod which means I can write the proportionality sign or symbol for that and write down in this way that, let me know, this is M. So which means that I can write down this: the total angular momentum is directly proportional to the angular velocity of the rod, which means L total is directly proportional to omega, and the constant of proportionality is 1 over 3 ml square, which you can see here. Okay, so here, and this is the moment of inertia of the rod about the pivot point at the center of the rod. Moment of inertia of the rod, okay, about pivot point at the pivot point at the end of the rod. Right. And one thing to note is that the moment of inertia about the pivot uh, is greater than the moment of inertia about the center of the mass, on which you can okay, so this is right. And then I can write that the moment of inertia about the center of the mass sorry for that, so it is moment, so this is the moment of inertia about is given by 1 over 4, as we done the calculation above, which is ml square omega. Yeah, and the moment of inertia about the pivot and the moment of inertia about the pivot, which is at the end of the rod, which is coming out to be 1 over 3 ml square. Okay, so which is greater than moment of inertia about center of the mass, because you know this quantity is given by 1 over 3 ml square omega, whereas this quantity is given by 1 over 4, okay, ml square omega. That's why it's greater. This is now, this happens because of the mass of the rod. This is because the more mass of the rod is distributed further away from its end than from its center. Okay, so the more mass of the rod is distributed further away from its end than from its center. So that's why the moment of inertia about the pivot is bigger, because more mass is distributed away from the end of the rod, because the pivot is located at the end of the rod. So that's why this quantity is bigger than this quantity. And this also makes it more difficult to rotate. So it is more difficult to rotate about the end. So rotating the rod about the end is more difficult than rotating it about the center of the mass of the rod. So I can write it that this is because more of the mass of the rod is distributed further away from its end than from its center, thus making it more difficult to rotate the rod about the end. So rotating the rod about the end where the pivot is located, it is more difficult than rotating the rod about the center of the mass, where center of mass is at the center of the rod. So another way to explain or another way to obtain, not explain, another way to obtain the angular momentum about the pivot. So there is a second way to obtain, another way to obtain the total angular momentum about the pivot. Okay, so what is the other way? It is if you integrate down the rod starting from the pivot point. So if you do that, then the differential L total is given by, so if you are considering this rod here, this is vertical line, so this is the rod. So you are integrating from the pivot point, okay? And suppose this point is here, not at the center necessarily. So here, for instance, so this distance is R, okay? And so this is, so in that, this is given by R dp. dp is the differential momentum of that a small portion of the rod here which has got the mass dm. Okay, so dp will be velocity time dm, and it will be where r and p vectors are of course perpendicular. Okay, so now I can obtain via this different route. So it will be dl total will be r time dp, and dp is nothing but vdm. Okay, so if you dp is the differential momentum, so it should be v. So again, this is the v, okay, and dm, velocity time the mass is dm and the velocity is, so this is dp, and this one can be written as r times, now this can be written as r time v dm, but v can be written as r omega dm, this is v, okay, and this can be written as r square omega dm. Now if you integrate this in this different way to obtain the L total, then it becomes r square omega, and but dm is given by lambda dr. Okay, because if there is a differential length associated to this mass m, then dm is the linear mass density time dr. Okay, so I can rewrite this r square omega, and then dm is lambda dr. So this then becomes lambda omega r square, and the integration is from 0 to L, not L by 2. Now you see the difference. So it is then the integration with respect to r. Okay, so this then becomes lambda omega, then r raised to power 3 over 3, 0 to L, and this is lambda omega and divided by 3, and this is L raised to power 3 minus 0, which is lambda omega L raised to power 3 over 3. So now this is your L total, okay, so which is 1 by 3 m. Okay, now I can write, so this is 1 by 3, if I rewrite it as, so okay, so this is draw, so 1 by 3 lambda omega L3. Okay, now if I rewrite it in this way, that this is 1 by 3, and now lambda is nothing but m over L. Okay, this is linear mass density omega L raised to power 3, and this then becomes, if you cancel one L, it becomes 1 over 3 m L square and omega. And so this is the total. You can see L total which you obtained previously, which was how much it was coming out, 1 over 3 ml square omega. But here you used a different way. You see here it was sum of the two things, okay, two quantities which you added up to obtain this. Whereas in this new approach you have integrated from the pivot towards the other end, okay, but you still end up in obtaining the same answer. So the two results, the two methods yield the same result in obtaining L total. Okay, now if you have got any questions, please let me know. Are there any questions? Okay, thank you. We will see you in the next lecture. Thank you.